This is part 7 of a series on generative adversarial networks. In this video, we will implement LSGAN models. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last video, we took a closer look at the learning mechanism of an LSGAN. In this video, we will implement the LSGAN and LSGAN models. Now let's implement an LSGAN model in code. Generate a dataset consisting of 8 Gaussian distributions, arranged in a circle like this. This is the real data, the same one we used to implement the standard GAN in the second video of this series. When applying a standard GAN to this dataset, mode collapse is observed. Let's see if an LSGAN can improve this phenomenon. Create a discriminator model. The discriminator contains 3 fully connected layers. The final layer contains 1 neuron and no activation function, meaning a linear activation function is used. The discriminator of a standard GAN uses the sigmoid activation function for binary cross-entropy loss. But the discriminator of an LSGAN does not need to use the sigmoid activation function because it uses the least squares loss. The discriminator will learn to regress to 0 and 1, otherwise it will pay a penalty. Next, we create a generator model. The generator also contains 3 fully connected layers. This is identical to the generator model of a standard GAN. Next, we write a custom class to create the LSGAN model, just like we did when creating the standard GAN model before. This class takes as input a discriminator model and a generator model. Additionally, it takes the parameters A, B, and C for the LSGAN loss as input. We will use the RMS prop optimizer to train the models D and G. Next, we write a function to compute the loss of the discriminator. The input X and Z are the real data and random noise, respectively. GZ is the output of the generator for Z. dx is the output of the discriminator for x, and dgz is the output of the discriminator for gz. We use this formula to compute the loss of the discriminator. Next, we write a function to compute the loss of the generator. We use this formula to compute the loss of the generator. We define a list of metric objects for the discriminator loss and the generator loss. Next, we define the train step method. First, we update the discriminator. Sample random noise Z from a uniform distribution. Update the parameters of the discriminator to minimize the loss D. We updated the discriminator twice per train step for more stable learning. We then update the generator. Resample random noise Z from a uniform distribution. Update the parameters of the generator to minimize the loss G. Now we create and compile the LSGAN model. As we saw in the last video, there are 2 ways to set the parameters A, B, and C as follows. The paper notes that in practice, these 2 methods show similar performance. However, for this dataset, the model using the first method did not perform well. So we'll use the second method. We write a function that observes the distribution of real data X and fake data G of Z. Next, let's fit this model to real data and observe the distribution of fake data. Fit this model to the real data. The number of iterations is set to 50. We store the losses measured during training in two lists. We observe the distribution of the real data X and fake data G of Z. Repeat this process 20 times. Finally, let's check the loss history of the discriminator and generator stored in the list. The loss history of the discriminator measured during training is as follows. After 1,000 iterations, the loss converges to about 0.25. The loss history of the generator measured during training is as follows. After 1,000 iterations, the loss converges to about 0.12. After 50 epochs, the distribution of fake data is as follows. The red dots are fake data G of Z generated by the generator, and the blue dots are real data X. After 100 epochs, the distribution of fake data is as follows. The fake data is now a little closer to the real data. After 200 iterations, the fake data became slightly more similar to the real data. After 1,000 repetitions, the fake data became very similar to the real data. In the standard GAN implemented in the second video, mode collapse and mode hopping phenomena occurred like this. We can see that these phenomena disappear in our LSGAN model. Let's run this code. Fake data is getting closer and closer to real data. We can see that no mode collapse or mode hopping occurs. Next, let's implement a small version of the LSGAN model that generates MXDL images. The architectures of the discriminator and the generator are taken from Chapter 4 of the book Advanced Deep Learning with Keras by Roel Atienza. Load MXDL dataset. Training an LSGAN takes a long time, so we will only use 2,000 images out of a total of 70,000. Create a discriminator model. This time, we will use the sigmoid activation function in the last layer. Even if you use least squares loss, you can still use the sigmoid activation function. Create a generator model. These models are the same ones we generated when implementing the LSGAN in the third video of this series. Next, we write a custom class to create the LSGAN model. This time, we will use the atom optimizer to train the models D and G. The rest is identical to the LSGAN class in the previous code. We create and compile the LSGAN model. Parameters A, B, and C are set the same as those in the previous code. Fit this model to the real data. To produce better quality images, we need more iterations with more data. But this takes a long time, so we only did 500 iterations with 2,000 images. And we observe the loss history during training. Finally, we use the trained generator to generate MNIST images. Let's generate 10 images. Sample 10 random noise Z vectors from a uniform distribution. Feed the Z vectors into the trained generator. Then, 10 fake images are generated. Visualize the generated images. Let's check the results. The changes in loss D and loss G during training are as follows. The loss history of the discriminator is like this. And the loss history of the generator is like this. The images generated by the generator are as follows. Images of various digits were generated. As we saw in the third video in this series, images generated from the standard DC GAN show a lot of digits 1, while images generated from the LSDC GAN show a variety of digits. This means that the mode collapse phenomenon is reduced in LSDC GAN. Let's run this code. We got the following results. Let's create some more images. The quality of the images isn't that great, but the mode does not collapse, and a variety of images are being generated. So far, we've looked at LSGANs. In the next video, we'll look at Wasserstein GANs.